Okay, so we obtain this expression here by forcing a conditioning here, using the fact that n of t minus s is independent of all the ij's and hence independent of this sum also. Why we do this is now going to be clear. So once we have this expression, note that this is a conditioning, therefore I can replace this L by n of t minus s. Okay, so I can make it a sum of ij's, j running from 1 to p minus s. And that's a good thing because that's something we already have in the right-hand side of star, star, star. We already get to see what is there in the right-hand side, and that's why this is a good sign. And note that this expression here, this entire sum, is just the unconditional probability of this happening. This is equal to this unconditional probability. So this is nothing but if you start with RHS, this is the RHS of right-hand side of star, star, star. If you start with that and then condition on n of t minus s and use law of total probability, that's precisely you're going to get this expression. So this is just nothing but this unconditional probability. And that's the right-hand side of star, star, star. So therefore, we have been able to show that the left-hand side and right-hand side of star, star, star are the same in the sense that, okay, so to be honest, the right-hand side and the left-hand side only deals with random variables, and both random variables, namely this random variable which is in the left-hand side of star, 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 and this one which is in the right-hand side of star, 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 they both have the same range, and their range is the set of all possible non-negative integers. And I've shown that for all non-negative integer k, this equality holds. This is equal to this, and therefore it shows that this random variable is equal in distribution with this random variable, proving star, star, star. And this completes the proof of 2 bar. So if we summarize what we have done, is precisely what was the idea behind why it should hold, why you should expect to hold. So this double conditioning argument essentially formalized the following heuristic, as I have said already. So the left-hand side of star, star, star is a sum of nt minus ns many Bernoulli P random variables, whereas the right-hand side of star, star, star is a sum of n of t minus s many Bernoulli P random variables. Nt minus ns has the same distribution as n of t minus s, and ij's, the Bernoulli random variables, are all independent of both these random variables, nt minus s and nt minus ns. Therefore, we should expect this to hold. Of course, this is not a proof, but what we did using the double conditioning argument is just to formalize this heuristic, this intuitive argument. Okay? So even though it was a long proof, but the gist of the proof can be written just like here in this part, what is written here, this heuristic. And note that in the conditioning, we have, other than conditioning, we have already used the independence of the increments and also the stationarity of the increments. We have used both here. And the fact that the increment is Poissonian has been already used in the other part of the proof of 2 bar. Okay? So, namely where we use the hen and egg problem. So in order to prove 2 bar, we actually need both the independence and stationarity Poissonian increments. All of these things we need. Okay? Okay, so now we have to prove 1 bar. Okay? So this 1 bar is essentially you take a k positive integer and then take non-negative reals t0 less than t1 less than t2 all the way up to tk. So essentially these are all positive reals except that t0 is allowed to be 0. k plus 1 many positive real numbers. We have to show that the increment random variables, namely n bar t naught, n bar t1 minus n bar t naught, n bar t2 minus n bar t1, all the way up to n bar tk minus n bar tk minus 1 are independent. This is the independent increments. What we will do is we'll sketch the proof when k is equal to 1, just for simplicity. So general case can be done using the same argument, but the notation is going to be much more complicated. The idea of the argument is still the same. So we are only going to sketch the proof for k equal to 1. Sketch meaning I'll leave an important part for you as an exercise. Okay, so to do that, let's take, so once k equal to 1, we just have to show that n of t naught and nt1 minus nt naught are independent. Right? Okay, so to this end, take two non-negative integers, n naught and n1, and then take a non-negative real number t naught and another real number t1, which is strictly bigger than t naught. So we have to show that these two are independent, which is same as showing this joint probability of n bar t naught and n bar t1 minus n bar t naught is same as the product of these two marginal probabilities. Okay. Now, of course, I have n bar of t1 minus t naught here, not n bar t1 minus n bar t naught, but these two guys have the same distribution anyway. Okay, that's the statement of 2 bar. The distribution of n bar t1 minus n bar t naught is same as n bar of t1 minus t naught. That's 2 bar. So therefore, here I could have easily replaced, I can easily replace in light of 2 bar, this guy by n bar of t1 minus n bar of t naught. So therefore, once we show this, the independence of these two random variables is proved. This one and this one is proved. Okay? Because although we have n bar of t1 minus t naught, by stationarity of the increment, which has already been established by the double conditioning argument, this is actually, you can write, this is also the probability of n bar t1 minus n bar t naught is equal to n1. Okay. This is same as proving. So this is just, I've written these two things longhand. I've expressed all of these objects longhand. So therefore this is same as proving these things, this star. This is what I'm going to keep as an exercise for you. Namely, using a double conditioning argument similar to the one used in the proof of star, 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 show that this star holds. Note that this is a different kind of star. Okay, this star holds. The argument is very similar to what we have done. So this is an exercise for you. As I said, I'm only sketching the proof in the k equal to 1 case for simplicity. In the general case, when you have to prove all these k plus 1 many random variables are independent, then you have to actually use a k plus 1 fold conditioning as opposed to a double condition.